In this video, we're going to talk about orthogonality. We're going to find the inner product of two vectors. We're going to determine if two vectors are orthogonal. We're going to find the norm of a vector. We're actually going to find a non-standard unit vector, and we're going to use the Gramschmidt process to find an orthogonal set. Since we are working with complex numbers, and we typically work with the real, but we are actually looking at the bigger numbers, the complex numbers. Now would be a good time to go refresh some basic properties of arithmetic with complex numbers, because we always start in this class with the larger number set, which is complex, and then we go into the smaller set. If I want to talk about complex numbers, complex conjugates, we are looking at a complex conjugate of a column vector. Suppose U is a vector from the complex numbers, then the conjugate is denoted as U with a bar over the top, and the way that we define it is that each individual entry here will be the conjugate of the previous entry. So if I have 2 plus 3i, my conjugate is 2 minus 3i. If I have 5 plus 2i, my conjugate is 5 minus 2i. If I have negative 3 plus I, my conjugate is negative 3 minus I. No surprise there. We get some theorems from this. One of the first theorems is that we can find the conjugate by adding the two vectors first and then doing the conjugate, or I can do the conjugate of each one individually and then add the two vectors afterwards. So this is the first one we have. The second one we have is if my scalar is a complex number and I'm multiplying it by a vector that is filled with complex numbers, I can go ahead and do my scalar times each entry and then do the conjugate of that, or I could conjugate each one individually and then do the multiplication. The next thing we're going to do is talk about what the inner product is. So we're given two vectors, u and v, in the complex where my entries come from the complex numbers. Then the inner product is the scalar quantity where I have the conjugate of the first entry of my first vector multiplied by my second entry, or my first entry in my second vector. And when I do this, what ends up happening is I'm going to get a scalar quantity, which is going to be a complex number. So let's do an example of what this inner product means. And I just want to say that if we are looking at just real numbers and we're in a Euclidean space, you sometimes might have heard this as the dot product. So the notation that you see here is u comma v with these brackets. And what that means is I'm going to do the conjugate of my first vector, so it's 2 minus 3i, and it's going to be multiplied by the entry in my second vector, which is 1 plus 2i. And then plus the conjugate in my first vector in the second position, so the conjugate would be 5 minus 2i, so 5 minus 2i. And it's going to be multiplied by the entry in the second vector in the second position, so minus 4 plus 5i. And then I have plus, and then I have my last multiplication here. The conjugate of this negative 3 plus I is going to be negative 3 minus I, and then multiplying by what's in the position of the second vector, third position. So 0 plus 5i. Now, when I multiply these together, and this is where you want to go ahead and do some refreshing, I'm going to distribute this through, and so this is nothing new in terms of the multiplication. When I do that first multiplication, this is going to be equal to 8 plus I. That is that first multiplication of those two complex numbers. And then when I do my second multiplication of the second set of complex numbers, so that's this one, what you're going to get for that is going to be plus, and that multiplication when I get done is negative 10 plus 33i. And then I'm going to do this last multiplication through, distribute and multiply and combine up like terms. and that's going to give me when I multiply it, 5 minus 15i. Now what I'm going to do is I'm just going to do my regular addition of complex numbers, and when I do my regular addition of complex numbers, I get 3 plus 19i. So that is the inner product of those two complex vectors. That's my answer. It is a scalar. It's a complex number, but it is a scalar. When we're working with real numbers, the whole inner product, or dot product, is so much easier. So when you do this multiplication, you're going to be doing the 2 times the 3. And it is strictly just 2 times the 3, because a complex conjugate of 2 plus 0i is 2 minus 0i. So the gist of it when I'm working with real numbers is I'm just multiplying the same numbers in the same positions. What I mean by that, if I'm doing v and or w and x, and I'm doing the inner product, I'm just doing 2 times 3. And then plus, I'm going to be doing 4 times 1, so 4 multiplied by 1. And then plus negative 3 times 0, so negative 3 multiplied by 0. And then I'm going to do the 2 and the negative 1, so plus 2 multiplied by negative 1. And lastly, my 8 multiplied by that negative 2. So plus 8 multiplied by negative 2. Now see how much easier this is when we're in real numbers? When I do all this and I add it all up, I end up with negative 8. So if I'm in real numbers, I am doing the conjugate, but if I have 2 plus 0i, because that's what 2 is in complex, its complex conjugate is still just 2 minus 0i, in other words, just 2. So I didn't have to do the shenanigans I had to do up here, simply because I'm working with a real number and not a complex number. So much easier in the real number system. When we are doing the inner product and vector addition, we know that we can do the inner product by first doing the vector addition and then doing the inner product of the result. Or I can do the inner product of the u and the w, and then the v and the w, and then add them together. So if I'm asked to find the inner product of these, here, I can first go ahead and do the v vector added to the w vector, and then do the inner product with z. So I'm going to do my v vector plus my w vector, which is 3, 4, negative 1, plus 0, 1, negative 3. This becomes 3, 5, and negative 4. Now I can do the inner product, so there's my v plus w. I'm going to do the inner product with that with z. So I'm going to take and multiply this and this. So I have 3 multiplied by negative 2 plus 5 multiplied by 1 plus negative 4 multiplied by 0. And so what I'm going to get is I'm going to get negative 6 plus 5, in other words, a negative 1. I get a scalar. I also could have done this by the inner product of the v and the z plus the w and the z. If it would have been easier, I could have done it individually and then added those two numbers together, and I should have gotten the same answer either way. All right, let's move on. Our next theorem is the inner product of scalar multiplication. We have these two vectors whose entries come from the complex numbers, and my scalar is also a complex number. Then I can take my scalar and multiply it by one of my vectors, and then find the inner product of those two resulting vectors. Or I can find the complex conjugate of my scalar and multiply it by the inner product of the two vectors. Similarly, notice the location of my scalar. My scalar now is on the second vector. So if I want to find the inner product of u and then my scalar times v, then it is different than the one up above because of the location. It is simply going to be my scalar multiplied by the inner product. So pay attention to where my scalar is if we're working with complex. Real numbers, we know that the complex conjugate of a real number is just the real number. So if I'm asked to find with real numbers the alpha, which is not that is not a vector, that's a typo there. So it's my alpha, which is a scalar multiplied by my vector, then I can do my inner product first and then multiply by 5, or I can multiply by 5 each one of these entries and then find the inner product. Now I'm going to work with smaller numbers, so the way I'm going to approach this is I'm going to do my alpha after I have done my inner product of these two vectors. So this is going to be 5, and then what's going to end up being inside here is this 3 times the 0, so 3 multiplied by 0, plus the 4 multiplied by 1, so 4 multiplied by 1, and then plus the negative 1 multiplied by the negative 3, so negative 1 multiplied by negative 3. And I'm going to multiply that answer by 5. So inside, I'm going to get 4 plus 3, which is 7. And then I'm going to multiply that by 5, and my final answer is 35. A lot easier when we work with real numbers. So on this one, we want to look at the inner product as anti-commutative. Suppose we're doing the inner product of the u and v being, of course, entries in the complex, and that should be both u and v coming from the entries coming from a complex plane. Then what I have is I have the uv is going to be equal to my inner product uv is going to be v multiplied by u, and then of course it's going to be the conjugate of that answer. So what we know is if we want to do uv here, then this is the same thing as what we found from before, from up above. But let's show you that that's what it is. So first I'm going to go ahead and do the multiplication. So I'm going to first do the inner product of u and v, then u, and then I'm going to find the conjugate of that answer. So now what it's going to be 1 minus 2i, and then it's going to be multiplied by 2 plus 3i. And then it's going to be plus, now it's going to be the negative 4 minus 5i, and it's going to be multiplied by 5 plus 2i. And then it's going to be 0 minus 5i, and now it's going to be multiplied by the negative 3 plus I. Now if you compare it to what we did before, we conjugated the first vector and multiplied it by the second. Now I'm conjugating the second vector, multiplying it by the first, and then I'm going to take the conjugation of that answer, and I should get exactly what I started out with. So when I did my first multiplication here, this one here, I ended up with 8 minus I. When I did this multiplication here, I ended up with negative 10 minus 33i. And when I did this last multiplication here, I ended up with the 5 plus 15i. Now when I add all these together, I end up with 3 minus 19i. Now if I conjugate this, so now that's what u inner product of VU is. Now to do the conjugation of that, this will be 3 plus 19i, which is what we had before. So what that means is order does matter, that when I am doing V times U, notice V times U gives me this. but not times. V, the inner product of V first, then U, is a different answer if I would have done U first, then V. So order matters. Let's take a look at the next problem. Just want to make sure I don't rotate this when I move up. We are looking at the definition of the norm of a vector. What the norm of the vector is, it is, by the definition, it is going to be each individual entry squared, and then I take the square root of that answer. So let's take a look at this first example. We'll do it with complex, and then we'll do one where it's not complex. So I'm going to first find each individual entry, and I'm going to square it. So I'm going to do 2 plus 3i, and it will be squared, and then plus 5 plus 2i, and then it will be squared, and then plus negative 3 plus I, and then I'll square it, and then I'm going to take the square root of that answer. So what I'll end up with is 4 plus 6i minus 9, that is this first multiplication out, and then I'm going to have plus, and this is all underneath the square root, then I'll have 25, and then plus 10i, 20i, should be 20i, and then minus 4, and then I'm going to have plus, and that's this multiplication out. I'm going to have 9 minus 6i minus 1. This is all underneath the square root. And when I add up like terms, I'm going to get 26, that's my real part, plus 20i. And there is the norm. Now let's use an example where we have a vector that is real. So we'll use real entries. Let's do 1, 2, and 3. So this is, we're going to call this W, my vector W. The norm of my vector W is going to be the square root of 1 squared plus 2 squared plus 3 squared. And this is going to give me the square root of 1 plus 4 plus 9, which is the square root of 15. So sometimes what ends up happening is I don't get a nice number. I don't always get a nice integer number. Sometimes I end up with a complex number underneath the square root if I start out with complex numbers. Sometimes I end up with a number that does not have a nice value. Square root of 15 is not a nice value, and that's okay. So we have this theorem that says the inner product of the norms. Suppose U is a vector from the where its entries are from the complex numbers. Then the norming squared is going to be its inner product of itself. So we know what U is, the norm of U. We found from before is the 26 plus 20i. So then if I square that, I'm going to square that. So I end up with 26 plus 20i. And that's it. So once you found the norm, if you square it, it's going to be the same thing as if I would have done the inner product of itself with itself. So, and you should verify that yourself. Similarly, if I did the same example here and I wanted to find the norm squared, it's just going to give me 15. Just something to think about. All right. So what ends up happening, because of the fact that the positive inner product, because U, again, is a vector whose entries come from the complex numbers, that when I do the inner product of itself with itself, it's always going to be greater than 0. And that's because, and it makes sense, right, that I have something squared should be a positive number. Okay, now we're going to go on to what it means to be orthogonal. We say two vectors are orthogonal as if their inner product, when I multiply them together, is 0. Not the 0 vector, just 0. So when I do my inner product, it is going to be, and I have to pay attention, is I'm going to do u and then v. So I'm going to do u on v. This will be equal to the conjugate of my first vector, so 2 minus 3i, multiplied by my second vector, first entry, and then plus my conjugate of my first vector, so 4 plus 2i, multiplied by 2 plus 3i. I'm going to keep going. And then I'm going to do plus, and then my next one will be 1 plus I, and I'll multiply it by, that should be the conjugates. So 1 minus I, and then 4 minus 6i, and then lastly plus the 1 minus I again, and then I have it multiplied by 1. So when I do all this, I get my first complex number. This first multiplication is negative 1 minus 5i. That's that part. And then plus, so plus, my second complex number is 2 plus 16i. That is that number. And then I have plus the negative 2 minus 10i. That is that number. And then, of course, I just have plus 1 minus I. When I add these all up, I end up with 0. So what I know is that these two are orthogonal to each other. What orthogonal means is that they're perpendicular. So orthogonality is the same thing as perpendicular. Let's take a look at my next example. Nice real numbers. We like it when we have real numbers. It is simply going to be 1 multiplied by 2. That is the 1 multiplied by 2. Plus the 2 multiplied by negative 1, the 2 multiplied by the negative 1, plus the negative 1 multiplied by the negative 3. So negative 1 multiplied by negative 3. This is my inner product of v, not u, v, erase that, v and w. This gives me 2 minus 2 plus 4, plus 3. This does not equal 0. This equals 3. So these are not orthogonal. So those are not orthogonal. A quick way to check is just to go ahead and do the inner product, and it'll tell you whether or not it is orthogonal or not. The next definition that we want to address is the orthogonal set of vectors, definition of orthogonal set of vectors. So when we're talking about an orthogonal set of vectors, that means that each one of my pairs are orthogonal to each other. So I would check each individual pairs, whenever I does not equal j. So what that means is, let's do an example. Let's check to see if these are an orthogonal set. So the first thing I'm going to do is do these. I'm going to call this u1, I'm going to call this u2. So I'm going to do the inner product of u1 and u2. So this is going to be 1 times the 2, which gives me 2, negative 2 times the negative 1, that's going to be plus 2, and then the 1 times the 3, that gives me plus 3. So I can tell right away that these are not an orthogonal set by just doing my first check. Had that equaled 0, which it doesn't, but had it equal 0, then I would have had to do the check with the u1 and the u3. And had that equal 0, then I would have had to do the u2 and the u3. And then I had to make sure that every combination are orthogonal to each other. This one, we just do the first set and we know it is not orthogonal. Let's take a look at our next definition. We're now going to define a standard unit vector. The way it's defined as a standard unit vector in the real numbers is that if you were to actually put these vectors into a matrix, then you would have something that looks like this. And if you're thinking, wow, that looks an awful lot like the identity matrix, then you would be correct. So basically, the standard unit vector is going to have a form that looks like this. 1, all the way down to however many zeros you have. The next one could be 0, 1. And then the next one would be the one moved down into the next position. So that is the standard unit vectors. If I want to find the standard unit vector in the R2, the two standard unit vectors would be a 1 and a 0, and then a 0 and a 1. If I want the standard, and that should be R2. If I wanted the standard unit vectors in R3, then it would have been 1, 0, 0, 0, 1, 0, 0, 0, 1. So that's what it means to be a standard unit vector. Now notice in R3, I have 3 positions, first, second, and third, and I end up with 3 possible standard unit vectors in R3. One in the first, one in the first position, a 1 in the second position, and 1 in the third position. I don't have to have all 3 of them, but this is the 3 unique standard unit vectors in R3, just like this is the unique standard unit vectors in R2. If I'm asked to find non-standard unit vectors, or I'm just asked to find the unit vectors, non-standard, then what I first do is find my norm, or the modulus. After I find my norm, or the modulus, and U hat is one of the ways that we note unit vectors, then I take my modulus, and it is now a scalar, and I divide it into each one of the individual entry points of my original function, or my original vector. So I'm going to do my modulus for W, which is going to be the square root of 4 plus 1 plus 9. So this is the square root of 15. My unit vector for W is 1 over the square root of 15 multiplied by each one of these entries. And this will give me a unit vector going in the same direction. If I want it going in a different direction, then I would have a negative 1 over 15, 1 over the square root of 15. So this is going to be 2 over the square root of 15, negative 1 over the square root of 15, and then negative 3 over the square root of 15. And so that is my unit vector, non-standard unit vector. Let me just make that a little bit better, going in the same direction as my original vector. Let's take a look at our next theorem. It says orthogonal sets are linearly independent. Cool. Nice. That's nice. Linear independence. And there is a way in which we can find an orthogonal set of vectors. And the way that we find an orthogonal set of vectors is called the Gramschmidt process. So use the Gramschmidt process to find an orthogonal set to this set of vectors. So I'm assuming to start out with that this is not going to be an orthogonal set, but they're asking me to find an orthogonal set of vectors. So let's do the Gramschmidt. Now, let's get our notations. This is V1, this is V2, this is V3, because that's how I label my initial set. So I have this set of vectors. I do need to check to make sure that these are linearly independent, so let's just do a quick check. So let's throw these into a matrix here and make sure that they have linear independence. Now I can't use my quick check of the number of entries, the number of vectors and all that stuff. So I do have to put this into a matrix and do the RREF just to ensure that these are linearly independent. And my matrix in RREF form is 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0. And because the number of pivots equals the number of vectors that are in my set, we know that these are linearly independent. I have 3 pivots and I have 3 vectors. Now, Let's do the Gramschmidt. So the first thing is that V1 is equal to U1. So right out of the gate, I know what my first vector is. To find my next vector in the orthogonal set, it will be U2. U2 will be equal to V2, that's this vector, in case you're getting lost, minus the inner product of U1, which is V1, multiplied by V2, or not multiplied, but the inner product of, and then divided by the inner product of U1 with itself, in other words, the modulus. This will be a vector, a scalar for the vector, and then it's going to be multiplied by my U1, U1. My U3 is going to be equal to, using the Gramschmidt process, is going to be V3, this is my V3, minus, it will then be U1 with its inner product with V3, divided by the U1 crossed with itself, not crossed, but the inner product. I want to say inner product. It's not crossed, it's the inner product. In other words, it's the modulus. And that's going to be multiplied by U1. And then, again, U1 is the same thing as V1. And then I'm going to do the next one, which is U2. So I need to find that from my previous, before I can go on to this one. And V3, and that inner product, divided by the modulus of my U2, so I have to still find U2, and then that's going to be multiplied by U2. Now that's all I need, is these three pieces, because the linear sets, if you look at the formula here, is I always go to one less than what I want. So if my index is 3, then I'll go to the U2 here. If my index is 4, then I'll go to the U4 here. So this index also tells me how many terms I need when I do the Gramschmidt. It helps me keep track. If my index is 1, I expect 1. 2, I expect 2 terms. 3, I expect 3 terms. So here's 1, here's 2, and here is 3 terms. So you see what I'm going to need. I'm going to need a bunch of things to be able to find it. Now, my first one's easy. My U1 is my V1, so I already got my first vector in my orthogonal set. I will need to know the modulus, so I'll need this. I'm going to need the modulus of U. So I'm going to do the modulus of U1. And so U1 is my V1. U1 is V1. So I'm going to do the modulus, so it's going to be -1 squared plus 2 squared plus 4 squared plus 2 squared, and it's all underneath this square root. And so this is going to give me 1 plus 4 plus 16 plus 4. This is going to give me the square root of 25, or just 5. So I've got this replacement. Excuse me, I don't have that. I have this replacement. I also need, for my first U2, is I'm going to need the U1 crossed with V2. This is the same thing as V1 crossed with V2. Not crossed. It's not crossed. It is inner product. Keep saying crossed. It is inner product. Inner product. So it is the inner product or dot product. So let's go ahead and do that multiplication. It is -1 multiplied by 3, so -3. 2 multiplied by 3, so +6. 4 multiplied by -1, so -4. And then the last one, which is 2 multiplied by 3, which is 6. So this is going to be 3 minus 4 is -1, 3. So -3 plus 6 is 3. Minus 4 is -1 plus 6 is 5. So now I have got this piece. So I'm actually ready to do this U2. This is going to be V1 or V2, which is the 3, the -1, and the 3. Let me erase this so you can see where the numbers are coming from. And let me erase this over here because I'll need this space. And that will erase, okay. So then it's going to be minus my u1 with the inner product of v2, which is 5. So this is going to be 5 over 5, because that's the modulus of u1. And then it's going to be multiplied by my u1, which is my v1, or in other words, my first vector. So negative 1, 2, 4, and 2. When I do this, I'm going to find my u2. So remember, 5 over 5 is 1, so I don't have to worry about that. So 3 minus a minus 1, and that's going to give me positive 4. 3 minus 2 is 1. Negative 3 minus 4 is negative 5. And 3 minus 2 is negative 1. So I have found my second vector. So now I can use that second vector to fill out the second piece. So to do this one, I'm going to need my u1 with v3, that inner product. My u1 is my first vector. And so, again, my u1 and my v3 is going to be negative 7. So negative 1 and 3 is negative 7. And then plus 6, the 2 and the 3 is the plus 6. And then it's going to be minus 24, the negative 6 and the 4, so that's the negative 24. And then my last one is going to be 8, and that comes from the 4 multiplied by the 2. Okay, so this scalar, which I need for this part, is going to be negative 6, or negative 7. So negative 7 plus 6 minus 24 plus 8. And end up with a negative 17. Negative 17. So we know we've got that piece. We already have that piece from before. The next thing I'm going to need for this one is I'm going to need the inner product of u2, which I've just found, with v3. So this is going to be this 4. This is my u2. Remember, this is my u2. I'm going to cross it. Not cross, man. I'm going to do the inner product. I want to say cross, but it's not. It's not the cross product. It's the dot product, if you want to think of it that way. I'm going to do 4 multiplied by that 7. It's going to give me 28. I'm going to do 1 multiplied by the 3. That's going to give me plus 3. I'm going to do the negative 5 multiplied by the negative 6. That's plus 30. And then I'm going to do the negative 1 multiplied by the 4. That's minus 4. This is going to be, so 28 plus 3 plus 30 minus 4 is going to be 57. So now I've got this piece. The next thing I need to do is find the modulus of u2. So I need the modulus for u2. Remember, my u2 is the 4, 1, 5, negative 1. So 16 plus 1 plus 25 plus 1. So 16 plus 1 plus 25 plus 1 is 43. So the square root of 43. So now I've got that piece. All right. So this is going to be equal to, now that I've got all the pieces in place, this is going to be equal to my third vector in my original set, which is 7, 3, negative 6, and 4, minus, I need the inner product of u1, v3. u1, v3 was negative 17. So minus a negative 17 over. I need u1 with itself, the inner product with itself. We know that's 5. That's still 5. And then it gets multiplied by my u1, which again is still my first vector. So negative 1, 2, 4, and 2. Then I'm going to have my last piece, which is minus, so minus. And it is U2 crossed with V3, which we found to be 57, so minus 57 over, not crossed, inner product, and then U2 with itself, which is the modulus, and that's the square root of 43. 3, holy crap, 43, 4, 3, and then it's going to be multiplied, because it's a scalar, it's going to be multiplied by my U2. My U2 is 4, 1, negative 5, negative 1. So this is going to be equal to, and we're going to end up with some lovely numbers. I'm going to take 7. I'm going to add to it because this will make this a positive. I'm going to add to it the 17 over 5 multiplied by negative 1. So 17 over 5 multiplied by negative 1. And then minus 4 multiplied by 57. I'm going to get some decimals here. Divided by the square root of 43. So my first one is negative 36.2, we'll go with a 27. The way I did that was I did negative 7, this becomes a plus, 17 over 5 multiplied by negative 1, and then minus 57 divided by the square root of 43 times 4. That is my first position. Now I'm going to do 3. 3 plus 17 divided by 5 multiplied by 2 minus the 57 divided by the square root of 43. This one gives me 1.11. I'm going to do my next one, negative 6 plus 17 over 5 multiplied by 4 minus 57 over the square root of 43 multiplied by 5. So negative 6 plus 17 divided by 5 multiplied by 4 minus 57 divided by the square root of 43 multiplied by negative 5. And this one gives me 51.06. Now I'm going to do my last one. 4 plus 17 over 5 multiplied by 2 minus 57 divided by the square root of 43 times negative 1. So 4 plus 17 divided by 5 multiplied by 2 minus 57 divided by the square root of 43 multiplied by negative 1. And that one I get to be 19, I want to do that in blue, 19.49. So my orthogonal vectors are this. My orthogonal set T is going to be my first vector, which is negative 1, 2, 4, and 2. My second one, which is 4, 1, negative 5, negative 1. And then my last one, which is not very nice numbers, minus 36.27, 1.11, and 51.06, and 19.49. So those are my orthogonal set of vectors based on the Gramschmidt process.